that's what we're going to do now. Go is, our concurrency is about to get a gopher infestation. So I'm going to turn the mic over to James Martin from Little.
Hi, my name is James. I'm engineer at Little. And this is a talk I came up with a while ago about pitfalls in Go concurrency patterns. I took this talk and tried to, you could say, water it down a bit. I know we have a lot of new gophers that come here, people who are new to the language, and my original idea had a lot of code in it. And when you're new to a language and I throw up big blocks of code, it's really hard to absorb what's going on. I couldn't find a good way to walk through it. So this is going to be more of a talking talk, and hopefully enough space for Q&A to fit in there to get everybody up and running for the next talk on concurrency, which will have more code in it. So this I dubbed After Go Concurrency Patterns. There's some old videos out there, not that old, but still very relevant. You should probably watch them if you haven't. So we start off by watching Go Concurrency Patterns. It's a talk Rob Pike gave a few years ago. Excellent talk. One of the first things I saw on Go, and it really made the concurrency primitives in Go, made them make sense. It really clicked, and you're like, oh wow, this is going to be great. I'm going to write everything concurrently. And then you sit down and you start writing code, and you feel really good about how easy it is to write concurrent code. And then you want more. So you go back and you look at the talks, and you find Advanced Go Concurrency Patterns, which is kind of like Rob's talk, except more patterns and more really neat things you can do. And I'm not going to cover what's in these because you guys should just go and watch them at some point, because they do have some neat patterns in it. But what happens a lot is people new to the language will go and watch the first talk, watch the second talk. They're all pumped about patterns, and they can make anything concurrent. So we have these super gophers attacking their code with these concurrency patterns. And they read Effective Go, which everyone should read. It's on the Golang site in the basic docs. One of the tenets in there, Rob repeats it in his talk, is share by communicating. And in Effective Go it says, do not communicate by sharing memory. Instead, share memory by communicating. That might be stressed a little too much for some people's taste in Go, just because Go really isn't message passing. There's still shared memory. You can share pointers all over the place. And you kind of need to a lot. It's, you have to accept it as a pragmatic suggestion. But when that is hammered into your head, and you've watched all these Go concurrency patterns, that's the way you're going to attack your problems. That's your hammer at the moment. So where does this lead people? To something like this. Everything ends up in a Go routine. Everything is talking with channels back and forth. And they feel that mutexes are bad. Mutexes are the old way. It's how you worked with threads. That's how you got into the big tangled messes of concurrent code that you're trying to get rid of by moving to Go. So, as an example, this is my watered down abstract. I hate abstract examples, but I tried to make it as small as possible. So try not to think about what these things are called or what the methods are, just that the fact that we need to do things concurrently. So we've got a server, it's got some internal state. We want clients to start using it. The server has a do method, and that touches the internal state, so we need to protect that somehow. So our new Go superhero is going to jump in and add a channel. So instead of a method, our do is a channel now, and the server has a start method, and that here will loop over everything that comes in that channel and work on it. And so we solved our concurrency problem, but not really, because it's not really concurrent, because it still does things in serially as they come in on the channel, one at a time. So what we kind of have to do is we have to get rid of the error return value and have maybe have this send the error back through the request direct, which has its own channel to send the error back, because everything's happening concurrently. You don't want to wait on that. So now we have something like that. And so a request comes in, the little dispatcher here for the server sends it out on a Go routine, and the error comes back on the channel. And you're pumped. You're like, oh, this is really awesome. I'm doing stuff concurrently. There's no locks in sight. But then you're like, oh, well, my server needs to do something else. So we add a send channel, and you're going to want to cancel it, so you add a done channel. And we're sending off these Go routines multiple times, and things are starting to not quite feel right. And I've seen a bunch of code start getting into this state when it didn't need to, including my own. So this whole idea started a few years ago. One of my first Go projects, I wrote a message passing server, or a message queue. And we had a big system that relied on our message queue, and it sucked. So we're like, oh, well, let's write our own. I did survey the alternatives, and we had structured our environment so much to depend on certain features of our current queue that not having those features was a lot of work, and it was basically just as good to write our own. Around Beanstalk at the time and its protocol. So I started work on that, and this was my first big Go project, and I started Go routines, and I had these little dispatch loops, these little reactor loops. And then, say, in my code, like, this request might have needed to do something and communicate, so that would have its own little reactor loop. And then the request would need to talk back to the server, and they had reactor loops that had channels going back and forth. You end up with nested selects, cases that send off the different selects and different Go routines, and it starts to become a big tangled mess. And you end up with deadlocks, and everything you're trying to get away from with the old style of free-running threads and mutexes comes right back again, because you're not solving the problem, you're just calling it something else. You're calling it channels and select and Go routines. And debugging still will look like this. You have a big tangled mess, and when you have Go routines talking to Go routines over in channels, interdependent on one another, you're going to end up with deadlocks if you don't have an organized plan going in. So some things you would be like, oh, well, that's just a map. I don't need to synchronize it. I'm just mostly going to be reading from it. There are no benign data races. Don't even think about going there. If there's going to be read and write access, you want to synchronize that in some way. That little picture is from an awesome blog post that I'll put up a link for about benign data races and why there really are none. And it's okay, because others have felt this way too. This question just came up on Stack Overflow like a week or so ago, and I saw it, and I saw the title, and the first thing was like, what is he asking? Go routines or locks for concurrent clients? Like, Go routines and locks are two different things. But then I thought back to this talk idea I had, and I'm like, oh, he's running into the same problem. The other projects where people have brought up problems with their code, and I looked in there, and there's just these little reactor loops all over the place, and everyone's has these channels and a whole dispatch, and they're talking back and forth, all to protect some central central piece of code. So what we do is we go back to the basics. We bring in async mutex. And those snippets of the code kind of that I had earlier kind of hide some of the complexity to fit it on the screen. But this would be the safe, complete alternative using async mutex. This is a pattern you'll see a lot in Go. For those new to it, is you can take a mutex, embed it in whatever type you have, and anything that touches the protected state, you start off your method with a lock and defer the unlock. And then that do method is completely safe. You can call it with as many concurrent Go routines as you want. You don't have to worry about it. The access to the protected part of your server is serialized in all cases. It's so much easier than trying to fiddle with Go routines and communicating back and forth. So when do you use sync versus channels? If you're trying to protect something, protect one logical thing, use a mutex. It's not forbidden in Go, although they tell you to communicate with channels and select. Methods are a form of communication in the same way. Use a mutex to protect that one thing. If you look in the standard library, you'll see a couple hundred mutexes throughout the code there. Everybody, once they get going in Go, you need them. It's so much easier than using just channels. If you're synchronizing concurrent processes, aka Go routines, things that are happening, use channels. They provide synchronization points. They provide communication. Don't forgo them altogether, but use them for the communicating part of your concurrent system. Don't use them specifically just to protect one thing. Of course, you can always find exceptions to rules like that. So we go into the sync package. We have a sync mutex and sync wait group. These will probably be what almost anyone needs from sync. You can get away with just using those two, but you'll probably want to hit those two at some point. An example of using a wait group. We have a little function here, do something. It's going to print something. We want to start off 5 of those, but we need to synchronize when they're all done. We could use channels, we could have them communicate back, but the wait group does that for us. And you'll use this all the time once you start running a lot of concurrent code. And you can see what happens. It's not unsafe to unsynchronize them or not wait for them, but in this case, we run off the end of main and nothing happens because the program exits before any of the Go routines get to run. So if we wait for them, they're dispatched, we wait on them, they complete. A few more advanced things in sync, but still very useful. They're synced out once. If you ever want to do something just once, you don't have to fiddle with locks and flags and stuff. There's once for that. It takes a function and it will make sure that it's run once. It's not hard code. If you're ever in a situation where you don't understand how something in Go works, dive into the source code. The source for most of it's very approachable, although over time as it gets optimized, it gets a little bit more obtuse, but a lot of it is very easy to walk through. Sync has a few tricky parts in it. But you can see things like synced at once where they how they work and how they can trigger something to happen once and get that code out of your code. You can just pop that in there and do it once. Synced at condition is allows a whole bunch of things to wait on a single condition. Sync.pool gives you a sort of a safe free list. You can put things in and take things out, anything you want. And sync.pool will handle that for you. I'm not really going to go into those anymore, but feel free to look into them. So my tips for writing concurrency: try not to write concurrent code. When you bring up a web server in Go, which is what a lot of people are using Go for, is network services. So you bring up your web server. It might not be apparent off the bat to someone new to Go, but your web server is sort of free concurrency. There is no, it's not like bringing up the standard lib web server in Python where everything is going to be one at a time. You bring up your web server and it can handle whatever you can throw at it. You're going to get requests coming in simultaneously, doing whatever you tell the handler to do simultaneously. You have to handle that concurrency right away. But you've already got the concurrency happening. The Go routines are already split up. Your request is happening in its own Go routine. So a lot of times all you need when you're building your web app and you need to protect things is just a simple mutex between those Go routines. They don't need to communicate with one another. They're separate entities. Think about concurrency as a tree, not a mesh. Have sort of a branching out of your Go routines. Your web server starts up, and we'll use that as the same example. The server is running. The server accepts connections, and it sends off a Go routine to do its work. It has a starting point, and it branches out, and it comes back to that, and those return to that server. Once you have, yep.
So you run-of-the-mill web server.
Yep.
You don't need to do anything special when you're strong set up the web server, right? So you don't need to spin up Go routines for each request that comes in. It takes care of that for you automatically. Right?
Yep, it's already in its own Go routine. There's nothing left to do. People, a mistake I've seen a few times is in a handler, people will send off the work to be done on a Go routine. And they're like, why doesn't my server work? Well, the request is already in a Go routine, and you send it off to another Go routine and your request ended. And then the work's being done, but the server thought the request was done. Keep it in that Go routine. And it goes back to my first point is try not to write concurrent code. Put your code into the Go routine, write it procedurally. It's already parallel to the rest of the system. And until you need to put that work in some sort of background parallel processing, write it concurrently. Even if you think you might need to put it in the background, write it concurrently and wait to see if it's too slow to do it serially. A lot of things are faster than you think when you're doing it in Go and you're coming from a language like Ruby or Python. The HTTP requests happen in a couple milliseconds, minus everything else you're doing. There's a lot of times you don't need to try and parallelize that. You'll suffer a lot more in orchestrating that and communicating than you will just doing it serially. If you are going to have a lot of Go routines and they do need to communicate with one another, set well-defined waypoints where they can meet. Have a single dispatch loop, a for loop with a select. You'll see that a lot, and even though I use this as a counter example, you'll see this pattern a lot in Go code, a for select. People have even suggested making for select its own construct keyword. But basically you have a for loop outside of the select loop, and you just keep selecting over and over again on your channels. Whichever one comes in first, you handle it and go around the for loop again and handle the next one. Have sort of a master one of those running everything. If your Go routines are sharing channels and channels are dependent on other Go routines, that's where you run into deadlocks. That's where you get the same type of hard to track behavior as you would with just having mutexes and free running threads all over the place. Now, I hope I didn't try to water that down too much, and I got enough information out to you guys, and I left it open for questions because I know a lot of people are new, so I want to get people going. Yes?
Yeah, I want to know whether it's very good. So in the weight group example,
Yep.
It looked like, I'm not sure, it looked like everything came out in all of people, which I wouldn't expect if they were. Is that just an accident?
That is a complete accident. Yeah, then let me see if I have a good way of. I can bring it up. I just don't want to mess it up on the YouTube Hangout. Yeah, we'll just go with that. It is a complete accident in the way. Oh, 0, 1, 2. Yeah, well, that's the same thing. It's there's an environment variable you set in Go called GoMaxProx. You can set it from the within the runtime too, but it's preferred to set it as an environment variable, and it tells the Go runtime how many threads to spawn for Go routines. And since this is only running on one thread, it just happens to get scheduled in the order that you send them off. If I set GoMaxProx to 2 or 4, it would probably reorder those. Yes?
Is that related? Maybe that's because of the sleep there that you have?
Nope.
No?
Absolutely not.
Oh,
Yep, the sleep happens in that Go routine, and they all happen concurrently.
But aren't they all sleeping for different amounts of time though?
Nope, they're all sleeping for 1 second.
Sorry.
Yep, no, that's.
I was thinking there was an I.
Oh, in that, yeah, no, that's, yeah, they all sleep for 1 second just to make it so you can see something like it's doing some work. Yes?
I'm also about 10 days into Go, coming from a Java, Scala background. And especially from the Scala background, I mean, we handle concurrency by avoiding, it's only a problem if you have shared mutable state. And
Yep.
Functional language try to avoid the mutable state. So I'm just sort of curious what Go has to say about that.
Go aims to be pragmatic. There's no hard and fast rules in the language. It's very much get it done and get it done however you need to. So there is no real delineation between mutable and immutable state. You have methods can be assigned to a pointer to the type or the value of the type. That helps you sort of delineate because the value receivers won't be able to alter the receiver itself. But there really isn't anything preventing you from sharing state, having global variables, mutating them. It's completely up to the program's discipline to make sure it's done sanely.
Thanks for mentioning this. You can do all that, but it's still very idiomatic.
Yeah.
Right. Like it's supposed to kind of C++ all things.
Yep.
There are even things like the formatting are well defined. So there are definitely a lot of good idioms that you can say to have part of it.
Yes. Yeah. You'll find that working with Go just after a few weeks or months and reading other code, you'll see just a lot of patterns that just sort of make sense and people will use them in the same way. It becomes really easy to read other people's code because they will all use the same idioms in the code.
Right. I mean, 10 days into reading a company, kind of shocked.
Yep. Anyone else?
So, as a quick example, if say I'm writing some sort of ETL solution and I need to get a bunch of data and do something with each record about CSV or something like that. Would the standard approach be to just say, okay, I read a row and I need to go do a bunch of work with that row, and spin out the row routine and have a wait group. That doesn't go to my entire CSV. Xlib, would that be like a standard?
There'd be a couple ways to approach it. One is how you would do it in, say, Ruby or Python or whatever your favorite scripting language is to just do it serially. Read in the row, do the work, move to the next row. You can still do things lazily, reading them in and out on a stream. And that'll be the simplest and most forward way to do it. If you are going to spin off Go routines for that, then there's no there's probably a package to help with that someone's written. But you probably don't want to go off sending off a Go routine for every line in a file if you don't know how many lines you have. You may be defeating the purpose of the benefit of the concurrency just by overwhelming the scheduler with hundreds of thousands of Go routines all doing the same thing in parallel. And you would approach it the same way you would in other languages. You'd probably set up like a worker pool, which is that is a perfectly valid Go concurrency pattern covered in one of those 2 talks that I started up. You'd send off like 5, 10 Go routines, whatever works best for your workload and system, and they read off of a channel. And you send jobs in on the channel, and they whatever they need to do, send them back on another channel, or just write them out, however, whatever your workload is. But that'd be a worker pool sort of situation if you want to parallelize it.
Speaking of those 2 videos, does either or both contrast Java concurrency and Go concurrency?
No, they're pretty much from when it's been a little while since I've seen them both, but I don't think they try to contrast to any other languages. They're more of just a features of Go in each of them.
Yeah. I need to go, so I've never written it. Read some. The for select construct.
Yep.
So, is there the select construct?
Mm-hmm.
Is there a way to use that with sort of a variable number of channels that all have to match the same type of signature?
No. No, I don't think you can even do it. Yeah, because the reflect.
What was the question, James?
How to select on a variable number of channels. The question comes up every now and then, and I don't remember the best way to answer it. Usually, it's something like iterate over them in a slice of channels, but to select simultaneously on them, there isn't a way to do that without using sort of like a probably in one of those earlier talks, like a fan-in pattern, where you send out a bunch of Go routines to select on n number of channels and then feed the results back to you. But the select is being part of the language. Oh, does the reflect let you? Okay, I remember working with that and it being exactly like the select statement, but I haven't looked at it in a while. That's cool. Okay, so maybe you can select on a arbitrary number of channels. That's good to know. Yes.
Can you list maybe some more examples of concurrency? You mentioned like web server, you don't need to. So some places where I think it's
you'll definitely find those places when you need them. I'll say that, but
if you have like a long AI-based processing, you do like a batch upload or something.
Yeah.
And you want to like spin something on that.
Oh yeah. And yeah, anytime, like I said, I might have tried to compress this too much. Anytime you have a process you're trying to do concurrently, that is where the Go routines, the concurrency patterns come in. Put it in a Go routine, have it return a result on a channel. That's probably like the most basic concurrency pattern out there. And there's definitely places for more complicated ones where you're sending a channel over a channel that returns a channel back, and all sorts of convoluted ideas you can come up with. But it's really when processes need to happen together, then the concurrency patterns are perfectly valid. I'm not saying don't do that. I'm just saying that for your basic resource synchronization. That's really the core of what I was getting at, is that people take it too far, and there really is a place for just putting a mutex around some global variable.
So how do you decide, like, if you're approaching a problem and you don't know whether you should be using coroutines or not? What's a good sort of end step way of saying, well, yeah, this is a good sort of thing to introduce coroutines? Like what's a good task to try and run parallel or concurrently?
That's where I start with do not write concurrent code. Not really as a hard and fast rule, but write it without any concurrency first. See what needs to be moved off, where it makes the most sense. You get a feeling very quickly, because concurrency is so easy to manipulate in Go. Instead of just throwing it everywhere at the start and ending up with a big mess, write it serially, and then as you need things, just send them off into the background in one way or another. It'll usually, in most of my experience writing network services, it's just stuff that takes longer. You want to get out of whatever main loop you have, whether it's a HTTP request that you don't really need to wait on. You can do other stuff in the meantime. Put that in the background. You start to realize how easy concurrency is. You find the points where you're waiting for something and you could do something else. That's where you send it off.
Or perhaps you don't need to have an answer for
Yep.
like sending an email.
Yeah, you send that off, and if the in a lot of servers you return in Go, you return error values when you want to error something out. But in a server system, if you're sending off an email, there might be an error, but what are you going to do about the error if you get it back? So send it off in a Go routine, have the error logged somewhere, however you're managing that information, but you don't have to wait on it. Send it off in a Go routine and have it sent off while you continue processing whatever you're doing, ending the HTTP request. Yes?
I just wanted to add on to that one, because I've heard a similar idea a couple times from a couple questions of backgrounding something during an HTTP request. You need to be very careful with that, because if you background something and then you release a new version of your application and your hosting provider sends a term to your web application, it will stop the web server when all the web requests have been handled. But any background Go routine you've got running that's long running, you immediately exit, then it will not be guaranteed unless you're using some of the constructs like waiters, or you're waiting for a done channel or that sort of thing. So oftentimes it can make more sense to respond to the HTTP request, to leave that request open and processing your work, not to do it in a Go routine, because you will lose them, like we saw in the example when you removed away from .dev. All those routines just never actually exist.
Yep.
So your stuff will get killed.
Yeah.
It's not fire and forget.
No, it's not fire and forget. There's Ode doesn't magically make concurrency easy. It just makes it easier to write concurrent programs.
So in that vein, actually, the syscall package that's actually or basically it's kind of like trapping. So you can trap sig into a term. So a nice thing, that actually uses channels to basically create with the syscall package. You basically create a channel and you listen for something. So that's a good way to then do that.
Or it's a signal package. I think it's under OS Signal.
So there is a package that lets you do it.
And OS Signal is the values.
Yeah, exactly. Oh, yeah. OS Signal has the notify function.
So that's a
Go loves having lots of tablets.
yes. But yeah, so that's a good way to do to avoid the problem. That's something like that is to listen for the
And the two thoughts with that process are, one, you still need to track all your background processes, because when you do your track, you need to then wait for the whole thing back. So you still have to some sort of process. The second one is that it's not actually possible to tell an HTTP server to gracefully quit as it exists in the standard library, which means you have to exit on the HTTP server if you want to wait for all your other.
Yeah, it is a hard problem, and I approach the problem is you can make a good effort at closing stuff down, but you're not going to trap a signal 15. So if someone, or a 9, sorry, 15 is the normal term. You're not going to stop a 9. So if someone kills your program, it's gone. So you kind of have to handle the situation that it might terminate at any given point. Yeah, and yeah. Yep, exactly.
So,
yeah.
How do you find that Go helps you in any way to test programs that rely heavily on concurrency? Is there, I mean, that in and of itself is kind of a hard problem. But how does Go help or doesn't it help?
I haven't thought about that. I mean, it helps in the fact that it's easy to deal with, and it gives you the primitives to communicate between concurrent code. So if you make your units that you're testing are testable, whether they're concurrent or not, you can you can communicate with them in the tests the same way that your code works. Yeah, yeah.
To add there, the best way to test concurrent code is concurrent tests. And something that I'll do a lot when I have a unit that works concurrently is I'll take its collaborators, which is usually the current part of the unit. And for those collaborators, I'll use fake versions that implement channels for their method calls. And what that lets me do is when my collaborator goes and fans out and asks A for something, B for something, C for something, I can then say, all right, first let's have A respond, then B respond, then C respond. Okay, now let's flip it around, let's do B, C, then A. Let's have B return an error after A is successful, C is done yet. And if you back your face with channels, you can really twist it every way.
Yes.
Really kind of stretching it, venture into testing, debugging. One of the, and I'm the new guy here with my company, and I'm told, yeah, we don't have a really good way to debug Go. We're using scripts.
Yep.
Is that the state of the art here, Joe?
Yes and no. So the answer for everything. The probably the most recommended method is print statements. And that kind of comes from people who have written highly concurrent code in some other languages, like C, C++. It's hard to debug concurrent code. And I mean, sure you understand that. There isn't a debugger that can, as far as I know currently, that can follow concurrent Go code well. There are hooks to use GDB, but basically if the thread of execution jumps between threads, GDB kind of loses it. Because Go routines themselves can be rescheduled on new threads, and that really confuses the current debuggers. There's someone working on one called Delve that has a lot of features that are looking nice, but I haven't seen what the current state of that is. And a lot of people are like, what would a concurrent debugger look like? Where do you stop it when there's things happening at the same time?
Is it still print statements if you're not doing, you're trying to debug non-concurrent code? Or is it GDB?
You can use GDB if you want to step through stuff, but I think a couple of the IDE, there's a light IDE that I think incorporates a debugger that might be using GDB. I haven't looked at it in a while. I'm a print statement guy, so I can't really speak to that, but I know you can use GDB, and I have pulled it out a couple of times when I needed to dump some state, add an instant, get a stack trace from somewhere. Yes?
I just want to add something
may not like this answer, but I came from a C++, Java background, and I had this habit of like stepping through all the code I wrote to comfortable with it, and it's not possible. I think like IDE let you step through, but it's not always work like a just wacky stuff.
It probably uses GDB.
That I have to teach myself to write more test code. So every method that I test function that seems to solve the problem. So
I love that answer actually.
Yeah.
That was going to be my answer too.
Test it.
Concurrent code is more complicated, and the more complicated is the more tests you want. So the best thing for the tests is, like I was saying, if you have like channel fakes, you can get them all to like stop somewhere and not say anything at that point, which will lock your program. And when you get a deadlock like that, you get stack traces for every go routine, and it'll let you know exactly where it was at those points. You can also cause that to happen at any time with control /. It sends a signal to a run and go program that will
Sigquit.
stack trace, all of the current, all the stack traces for all the go routines. So if you get a test, even if you're like, sometimes I'm working with timer loops, so you won't even get a deadlock, you have deadlock. And then you can control / and see what your timer loops were waiting on, and then maybe what other like call went out and didn't come back because you forgot to have the fake respond to it or something like that. Okay.
Yeah, the Go stack dumps, stack traces are one of the best debugging tools you'll have, because it prints out the state of everything at its call. It shows if it was it shows if it was waiting in a select or in a block of code. It shows a lot of details that you can get whatever the exact state of the program was at that time.
Final question.
Yep.
Before we take a quick 5-minute break for our second speaker.
Mhm.
What's the correlation between an OS thread and a Go routine, and a Go program, cost of a thread? Because it's not one-to-one. Right?
Yeah, it's not one-to-one. It's set by your GoMax procs, which is either that environment variable set. It just reads it out of the environment, or you can set it from the runtime package. But like I said, it's preferable to set it from the environment. And that will set the max number of threads that the runtime will schedule Go routine, your Go routines on. So you could have 10,000 Go routines running at once, but if your GoMax procs is 1, you're going to have 1 thread working on 1 CPU core. So you'll have concurrent, but you won't have parallel. And you usually set that to whatever works for your system. Usually some more threads than you have cores if you want to try and fully utilize the system, but that's just, you need to test it, see how it works. And a couple points to finish up with. Like was said, testing your concurrent code is one of the best ways to make sure that it's as correct as you can get it. The test package has a parallel function that lets you run certain tests in parallel or not. That helps with checking your concurrency, because if stuff's going to fail when you run it together, then you have a problem with your concurrency primitives, whether you're fighting over a channel or you're going to deadlock on a channel or something. So run as much as you can at the same time when you're testing it. Can often fish some stuff out. The Go compiler has a race detector. Use it all the time. Don't use it in production because it does make bigger binaries and slow things down, but test everything with race, build everything with race, see how it works with race. It doesn't give you false positives. If it says something is wrong, fix it. And that's there's a new stress tester coming into Go 1.5 that will also beat on things for you. So you mix that with race and parallel and see what happens, and test.
Oh, thanks, James.
Cool.
Where are we on?
Hey guys, find our seats. So, Andy, you want to introduce our second speaker?
Yeah. All right. So now we've seen like some of the basics of concurrency. So now let's see how our next speaker, Andrew Guant, is going to apply that in the X client protocol. So here's the next speaker, Andrew Guant, also known as Burnt Sushi.
Hi, I'm Andrew. I guess I'm also known as Burnt Sushi. I'm going to be talking today about concurrency with Go, particularly in the XGB or the Xgo binding library. I've prefixed the talk title with experience report because I found it pretty difficult to try to tease out some principles of lasting value that I could communicate in a talk. So instead, I'm just going to describe how I took the Xgo binding that existed before I got my hands on it and used concurrent code to make it safe to use across multiple Go routines. And the structure of the talk is basically going to be some background about X, unfortunately, what the Xgo binding actually does. Then I'll say a failed attempt at making the Xgo binding write safe, and then I'll deliver the goods and show you how I use channels and Go routines to do it. So this is not going to be a talk about X, or at least I hope it's not. If any of you are not familiar with X, it was created in 1984. It evolved to version 11 in 1987, and the core X protocol hasn't changed since then. So I'm actually 2 months older than X11. So I'm going to absolve you from most of the details about X. This talk is also not going to be about sprinkling Go routines throughout my program and then increasing the number of Go max procs and then watching all of the CPUs stable on my machine. So really not about performance. It's really about writing a concurrent implementation that makes, in my opinion anyway, the code clearer and hopefully less error prone. So what is the Xgo binding? It's an implementation of the X client protocol. And by that, I mean it knows how to communicate with an X server at the byte level. So it can send requests and receive responses, errors, and events from an X server. It does things like create windows. It can map windows to the screen. It can hide them, receive keyboard input, mouse input, respond to user events, all at the very lowest level at the X level. So if you're familiar with the more popular Xcb or Xlib, which is the XC binding, you can think of XGB as basically a port of XCB. It does not wrap XCB, so it's pure Go, turtles all the way down, no C dependencies. A little history on Xlib and Xcb. Xlib predates Xcb by, I'm not sure, probably at least 10 years. Xlib has a manual implementation of the X-core protocol. XCB came around the turn of the century, I think, and realized that the X-core protocol could be described using XML, and could be taking the XML and generate an implementation of the protocol from the XML description of it. As a result, XCB tends to be extremely faithful to the core protocol, and you end up with really baroque signatures, but there's no abstraction boundary between XCB and the protocol that you're speaking. Whereas with Xlib, some functions that you call correspond precisely to one protocol request, but many functions that you call might actually correspond to several protocol requests because it's more convenient to do so. So yeah, most people don't use XCB or Xlib anymore. Usually people who are using it are people writing GUI toolkits or writing things like pagers or taskbars, smaller utilities, or if you're like me, you write window managers. So I do not intend for you to read this code or understand it, but I wanted to give you a smallest useful program that I could fit on a slide that uses XGB. What this program does is, or at least what it did last night, it may not work anymore, is print out the name of the window manager currently running on a Linux desktop. So the first pieces of it are just the imports. There's a magical constant here that I'm going to not explain. and connection. And then here's the part I want to zoom in on. So there are 2 X requests going on here, and you can see some of the C influences in the function signatures. But basically, the first request is saying, I want to intern an atom. An atom is basically a number that stands in for a string. So when you're communicating over the network, you have to send numbers instead of strings. The next request is getting a property on a window. The name of that property is represented by the atom, that WM name. And then finally, prints out the name of the window manager. The 2 things that I want to point out here are atom cookie and prop cookie. These things you can think of are, it's like a contract, or that when you get a cookie, it's sending a request to X, and at some point in the future, undetermined amount of time, it will return either a response or an error. You can think of these as like a promise or a future or an MVAR or something, a contract that says, I'm not going to sit here and wait for the round trip to the X server for a response. Instead, I'm going to let the programmer choose when the round trip happens, which is right here. Atom cookie.reply sits and waits for the X server to respond. I'll be re-explaining this throughout the talk, so if you didn't catch all of it, that's okay. Here's another kind of example, different flavor to it. This is extracted from code that sends images to an X server with the intention of putting the images somewhere on the screen. By default, the maximum request size of an X request is 64 kilobytes. So if you need to send a bigger image than that, you've got to send the image over in pieces with multiple put image requests. Ideally, you would want this to be fast. Here, the put image request calls check, which means it's going to send a request to the X server, and then it's going to sit and wait for the response of the X server. Then it'll come back around to the next iteration of loop, send image data, wait for a response. So it's doing a round trip after every single piece of image data that it's sending. Instead, what if we just send image data, or if we want to send image data, not have to wait for a response back from the X server, and continue sending image data without all the round trips in between? So the key difference between this code and the code before it is that there's an error check here, and there's no error check here. So am I just ignoring the error? What's up with that? In the X world, there are many times when you don't care if a particular request succeeds or not. Mostly the only reasonable thing you can do is log it to a log, just to print it to a log file somewhere and continue on and hope that the application stays alive. Okay, so a little bit of more history. Pre-Go 1.0, there was an Xgo binding library that I think was actually inside the standard Go library, probably in the experimental package. It was moved out around 2010. It was an incomplete implementation, but the primary shortcoming I want to focus on for this talk is that you cannot use an X connection for multiple Go routines simultaneously. This is important because you want to be able to use the same connection throughout your program for a variety of reasons. The most important one is that the X protocol is stateful. So it's not like HTTP. You can't just mix and match connections and expect that the same stuff is going to happen. There are other reasons, but I'm going to deflect those. If you're really curious about the nitty-gritty X details, I'll save that for the Q&A. So I wanted to give thread safety to it because I wanted to write a window manager in Go, and I ended up just rewriting just about all of the library, and that's where I am today. So before I actually start talking about my implementation, I have to describe to you the basics of the X protocol. The core protocol is pretty simple at a high level. Client sends requests, server sends events, which usually come from some sort of user interaction. Errors, every error corresponds to a request. Replies, every reply corresponds to a request as well. If a request gets a reply, it can't get an error. If a request gets an error, it can't get a reply. So they're mutually exclusive things. It's stateful. By stateful, I mean that the client and the server need to independently maintain state, and that state needs to be exactly the same. Otherwise, everything goes to hell. And the particular piece of state is a sequence number, and it's a way to match up requests with replies and errors. So the order of the requests that you send to the X server matters, because that's how the X server is going to tell you this reply corresponds to this particular request. To make matters worse, not all requests get replies. For instance, put image, there's no sensible reply other than success. X says, well, we're not going to tell you explicitly that that request was successful. Instead, you're going to have to infer that it was successful. How do you infer that it was successful? If you receive a reply from another request whose sequence number is greater than the request that you sent that didn't have a reply, then that implies that the previous request was successful. Okay, that was a multiple. Another way of saying it is, if you receive a response or an error from X and its sequence number is n, then all previous requests less than n, with a smaller sequence number than n, have been resolved. So either they would have gotten a reply, they were successful, or an error was sent to them. So as a programmer using XGB or even XCB, XGB is very, very similar in API to XCB. As a programmer using the library, you really want to be able to control when you ask for replies to particular requests, so that you can send a whole bunch of requests all at once and then ask for replies instead of doing a whole bunch of round trips in between. So a request that expects a reply is getting a property, which you saw earlier. This sends bytes over the wire, but doesn't wait for the response. This waits for the response. Or a request that doesn't need a reply. So when you map a window, there's nothing the X server can tell you about a successful operation other than the fact that it was successful. But as a programmer, I care if the window is able to be mapped. So I want to spend the round trip and ask for the window to be mapped, and I want to check to make sure that it was successful. So this will block and wait for X to either return an error or success. And then finally, as you also saw before, a request that doesn't need a reply or an error check. And that would be put image. So where do errors go? Put image can still generate errors. Like if you try to put an image to an X resource that doesn't exist or was destroyed or something of that nature, there's really, in your window manager or in your X client, there tends not to be a reasonable behavior other than sending it to a log somewhere. So what this will do is XGB will reroute the error to your event loop, and the code running the event loop will just emit the error and then continue on with what it's doing. So basically, the summary of this slide is programmer controls when round trips happen. So designing a solution, I think there are 3 key components to it, and the first one is sending requests. So how do you maintain the sequence number, the state that exists between the server and the client? Receiving replies and errors. How do you ensure that a particular reply or an error corresponds to a particular request that was sent? And then getting those replies and errors to clients of XGB. So first idea, this is roughly corresponds to the data structure that existed in the Xgo binding before I started work on it. So a cookie, in this case, also a promise or a future. Cookie tends to be the X jargon for it. It's just an unsigned 16-bit integer that corresponds to the sequence number. And the connection contains all our state. So it maps cookies to responses. If a response hasn't been sent for a particular cookie yet, then the pointer's nil. It maintains the current sequence number, and then the last sequence number received, which you'll see used in a second. So I said, how can I make this thread safe? Add a couple of mutexes, and our send routine is reasonably straightforward. We acquire a lock, We send the bytes over the socket. We increment the sequence number and return the old sequence number as the cookie. The idea being that if the client has the cookie, they can look up the response in that map. So receiving replies and errors. This is intended to be run as a Go routine. This reads a response from X. It could be an error or it could be a reply. We acquire a lock around protecting the map data structure. And we write the response we receive to the corresponding cookie. The response contains the sequence number, which means we can get the cookie, and assign the response value to the map. And here's the subtle bit. If you recall me mentioning that some requests have implicit success, this is the piece that implements that. So it starts at the last sequence number received and goes all the way up to the sequence number of the current response, and it marks all those responses as successful. I'm claiming that this is a marking of successful because the error is nil. The reason why I can do this is because the X server, the X protocol guarantees that if there had been an error or a reply in any of these responses, we would have gotten a response for it, and it would have been handled by this code. So update our last sequence number received, let go of the lock, and we process the next response. So the last bit is, how do we get the data to XGB clients? Well, acquire the lock and wait. I think my design is bad because how do we know that the response for this particular cookie has been filled in? So kind of back to the drawing board. Client doesn't know how to wait for a cookie. So what's the natural construct in Go? We need to incorporate channels somehow into our cookie. So instead of a cookie just being an unsigned sequence number, we'll add 3 channels to it. Each of these channels corresponds to the different types of requests that can be made. If a reply channel is set, then that means the request expects a reply. If the error channel is set, then that means the request is expecting an error. And if the request doesn't expect a reply, we still need a way to tell it, hey, the request was successful. X isn't going to tell you, but as the library, we'll assume that complexity for you, and we'll tell you when your request is done. So we can use nil channels to indicate the type of the request. If we want to create a cookie that expects a reply, or a request that expects a reply, we fill in the channels for the reply channel and the error channel. We leave the ping channel null. Similarly, if we want to check a request, then we can fill in the error channel and the ping channel, and we'll leave the reply channel nil. It's important to note that these are buffered channels. So if you're new to Go, when you make a channel, you can choose the size of the buffer. An unbuffered channel means there's no buffer to it, so that when you send on it, it will block until the receiver accepts the response. If you have a buffer of 1, it means that a sender can send a value on the channel. It won't block until the sender sends 2 values on the channel and the receiver hasn't received any yet. So when the Go routine that's reading responses from the X server sends values on these channels, we really don't want it to block. And since we'll only ever send 1 value on any of these channels, we set the buffer to 1, and that way it's always a non-blocking send. What about unchecked requests like put image? Set all 3 channels to nil, right? So if all 3 channels are nil, then we know not to do anything with it. It's not expecting an error. It doesn't care if it was successful or not. The client can't block on it. It's a kind of a send the request off and just hope it succeeds kind of deal. So our previous problem with figuring out how do we know when the response is done from the perspective of the cookie is easy to solve, because now our cookie contains channels. We can wait on either the reply channel or the error channel. Since only one of those channels will get a response to it. One of these will fill in, and we can return our value. Similarly, for the check case, this is a case that is a request that doesn't expect a reply but might have an error, but we need to be able to tell if the request was successful or not. So that's the read on the ping channel, the error on the error channel. This one, so cookie.con.sync is forcing a round trip. Why do we need to do that? Because if you send a request that doesn't expect a reply, and then you do nothing else, the X server won't say anything to you. So you'll sit here waiting on these two channels forever. Basically, if you don't have any other threads sending things to X, you'll deadlock. So if we force a round trip request, like ask for the current input for X, which is a completely benign request, it will force a round trip because it expects the reply. As soon as it gets the reply, go back to the old code. As soon as it gets the reply, this logic will get triggered, and the old cookie will get triggered as a successful response. So previously, we used a map to associate cookies with responses. So here's the old code I just showed you. Right, so we're saving a map from cookie to response. And this was a really key observation that it seems obvious in retrospect, but every cookie is visited exactly once, and the order of that visitation is first in, first out. So we have a built-in thread-safe queue into the language, and channels, again, come to the rescue. So old data structure, new data structure. We have a channel for our sequencing. We have a channel for our cookies, and we have a channel for requests. So generating sequence IDs is really easy. This is run in the Go routine. Basically, we increment the sequence number and send it on the channel. There'll be a consumer somewhere else that you'll see in a second that receives from this channel. If you want to ask me about overflow after the talk, that's fine, but I'm choosing to ignore it for now. So sending requests. The client might put a request on the request channel, and this is a single Go routine that's going to pop requests off that channel. It'll ask for a sequence ID. It's important that this is the only place that this happens, because if you have multiple requests being sent at the same exact time, then you might end up having a race between when you send your bytes and when you ask for a sequence ID. So then we have to figure out how we want to create our cookie. So we want to have a nil ping channel or a nil reply channel, or all three should be nil. And that logic is based on the request. So get property would have a reply, so we would use that. Map window checked would not have a reply, but the programmer is expressing intent of checking the error. So this would get invoked. Put image is not checked and doesn't have a reply, so this would get invoked. And this cookie is sent on the cookie channel. We'll read from that in a second. And then we send the bytes to X. So the last piece, which is processing cookies for each response. Instead of using a map to store responses with their cookies, we'll use our channel. So when we read the response, we'll pop cookies off of our queue, our channel. If we find the cookie that corresponds to the response that we just got, then we'll tell the cookie, okay, fulfill the promise, fill the future, fill the unbar. Great, stop processing cookies. If we saw a cookie, so this code will only happen if we see a cookie before we see the cookie corresponding to our current response. And if we see a cookie here, it means that it didn't expect a reply, it was successful, and didn't get an error because of the nature of the X protocol. So we'll ping the cookie and tell it success. And any consumer waiting on that check call for that particular request will be unblocked. Okay, so final example, just to kind of try to tie everything together. New connection for X, that's where the go routines for sequence IDs, sending bytes, receiving bytes, that's where all those are started. Those usually run throughout the duration of the program. Request sent, there's no blocking here, but you're getting a receipt or a cookie saying that at some point in the future that cookie could be fulfilled. And now the programmer chooses, okay, it's time to block and wait for a reply. Any number of requests and responses can come between these two lines. Okay, so in conclusion, I don't know if I have any like particular insights drawn from this example, but the key kind of like moment of clarity was realizing that the X protocol allows you to represent your cookies as a queue. And once I figured that out, using a channel seemed like the obvious solution. So, follow your data. How is your data flowing through your system? If you can find a way to represent that easily with channels and go routines, then go for it. There are a lot of complexities that I haven't mentioned today, mostly because I didn't think they were that interesting to the synchronization between requests and replies. But handling overflow is kind of tricky because you have to force a round trip at the right time so that you don't have sequence numbers overlapping each other. I didn't talk about events. Certainly, events come in from the X server, and those get sent on a channel. And I've talked a lot about requests that expect replies, requests that expect errors, requests that don't expect either. But there's kind of like that fourth thing, which is requests that expect replies, but don't care about the error. I don't know of any use cases for those, so I've left them out of the talk. But they do exist in XGB. It's used in at least 2 window managers, mine, Wingo, and there's another one called Tau WM. So I don't know if that qualifies as battle tested, but I've been using it for several years now, and things are running well. That's it. Questions? Yeah.
When you were figuring out what you wanted your API to be, what made you decide to choose an asynchronous API with reply and check instead of just exposing a synchronous API to the
That's a good question. When I was originally choosing the API, I like to say that I didn't choose the API. I mean, I wrote the code, so obviously I chose it, but the API of XGB corresponds precisely to the API of XCB. So this whole idea of having checked requests and having this kind of 4 states with replies and errors and checked or not checked comes directly from XCB. So I emulated their API. Whether that was a good decision or not, I don't know. Any other questions? Yeah.
I've never done any DirectX stuff myself, so I don't know how many calls are involved. Do you run into a problem with the overhead of CGO?
There's no C here.
Oh, okay. You're using the. I was thinking the whole time you're calling into something. Yeah, you're writing directly to the
socket. Yes.
The socket.
My window manager is pure Go, bottom up, bottom to top. Yeah.
So is that what we're running to manage the windows right now?
Yeah. It works. It's a hybrid tiling window manager. I don't know how many of you know about like things like OpenBox and Xmonad and Awesome and i3 and all that stuff, but I call my window manager kind of like the combination of OpenBox and Xmonad, which is traditional stacking window manager. So you can see here I can drag around my windows with window decorations, but I can also tile windows like this that all the decorations disappear, and I can use my keyboard to control the focus of the windows. Yeah, that's what the pitch for my window manager.
So explain to me the reason why you chose write the window manager? Is it a personal interest fact, or are you trying to sort of revolutionize the manager business?
Revolutionize is an overstatement, but my core reasoning was I think that the state of multi-head display on a Linux desktop is abysmal, and it's largely due to standards that were erected, decades ago. But basically, if you're on a Unix system like Mac or Linux, you have things called workspaces, and I think Mac got this feature recently. But if you have multiple monitors on most Linux desktops, when you switch your workspace, it switches the workspace across all of your monitors. And I hate that, especially because I have a triple monitor setup, and I want to be able to switch my workspaces independently on each monitor. And there are some window managers out there that support them, but they're pure tiling. And I kind of like having a stacking window manager sometimes. So I tried to write one in Python and failed. I forked OpenBox and had like a 1,000-line patch against that, and eventually got to be too much. And then Go came along, and I'm like, oh, I can do this with Go. That's my reasoning.
It's in Mac OS X now, but boy, it was a long time coming.
Yeah.
What?
The Windows that operate independently in the spaces.
Yeah. Yeah. Yep.
Yes, I think it was only the last release that
Yes.
happened.
In Mac?
Yeah.
Yeah. I remember reading about it. I'm like, they stole my idea, but it's been done long before I did it. Xmonad has it, among other things, other window managers.
Any other questions?
Yeah.
You said there were issues with the wraparound.
Ah, right. So, how to explain this? So sequence numbers are 16-bit integers defined by the core X protocol. I think there's a way to tweak that, but you need an extension, so I'll ignore that. So what was that?
Do you ever have that many outstanding requests?
Oh yeah, absolutely. There are tests that stress that actually, that very particular point, because you can spawn a whole bunch of requests, thousands, tens of thousands, whatever, however many you want, and XGB needs to be able to handle that. So what it does is, before it wraps around, and when it wraps around, it's not just like my client is wrapping around, it's also the server that's going to wrap around, because that sequence number has to be stayed safe. So just before it wraps around, I force a round trip request. And that basically resolves all outstanding cookies. And then the state is clear to wrap around. And that's basically how I solve that. Any other questions?
Good stuff.
Cool.
Thank you. So if this was your first time here, we encourage you to follow us on the Twitter account, Boston Golang, so you can follow all the latest news and stuff that we put out there. We also have a mailing list, which is not very actively used right now, but if you guys are interested, we actually just set up a Slack group. How many of you know about Slack? A few of you. So those of you who know about the latest and greatest thing on the interwebs, it's called Slack. Everybody's jumping on board. So if you want to check out bostongolang.slack.com, basically we're trying to sort of get an active participation, sort of public chat room, right? So you can jump on if you have questions, and if you want to ask the gentleman right here some questions, or if you want to ask James some questions, we'll make sure they get on Slack, right guys? Yeah. So so basically we're trying to grow the Golang community around here. So you guys are ahead. So you go ahead and
we'll try to set up like event widgets. In the meantime, either any tweak to the account or post on your post or something. So
Sweet.
And also, Jen would like to tell us about our next meetup.
Yeah, before you guys go, on May 18th, we're going to have a kind of fall meetup. It's going to be our first hands-on lab. So we're going to basically go through building a chat server and Go. So it should be pretty fun. We'll break up into teams and basically have a person at each table helping you out, walking through the curriculum. We do need volunteers, so if you have some Go experience and want to help out, let me know. Email me, jr@gmail.com, or when you sign up to the meetup, just kind of put in a different question and ask you whatever you want to know. But yeah, let me know if you want to know. Please come.
So basically what we're going to try to do is basically have a meetup like this one that basically addresses a certain kind of topic, right? And then 2 weeks later, we're going to have sort of a kind of workshop that builds on that meetup. That way, you basically can kind of use the knowledge you got from the talks into sort of a mini workshop type of thing. So it's a great learning experience. There's no speakers unless you want to go up and show what you kind of worked on. So it is collaborative. You can ask, for help, that kind of thing. So as a way to kind of help you learn and kind of get more comfortable with those. Next month's talk is going to be, or the theme is going to be on testing. Actually, our speaker is actually in this room. So Nick is going to be giving a talk on testing. Very knowledgeable on Go and testing. So definitely, if you kind of wondering how to actually, if you do TDD, if that's your thing, you want to come check it out, and I'm sure you'll be talking about that as well. If you're testing at all, right? You definitely want to come check it out. And the following workshop on that is going to basically leverage that talk, and basically we'll have a workshop that deals with testing. So we're going to try and do more and more of these things and kind of get the community sort of to come together and sort of build the community here in the Boston area. Hopefully get you all in high demand jobs.
And
So,
my company is hiring co-developers.
You know what I'm talking about? There it is.
You can go for infestation there.
So a few of us usually gather at the meet hall for a couple of beers. So if you've got some time, you know, hang out for a little bit, we'll be over there. All right, guys, thank you for coming. Awesome.
Terrible.